The other problem was show that alternating group is generated. Alternating group is only symmetric or even number of permutations, which means you cannot get just by transposition. If you have a generator, all powers of the generators should be elements of the group. If you put transposition as a generator, you are stuck, right. All powers includes even powers and odd powers. So, the better thing to start with the generator for a alternating group is minimal one is only a 3 cycle. Is that clear? So, your alternating group UN will involve identity and all possible 3 cycles. I am not writing, and then you will have powers of them, and then you can also multiply them. Okay. You can also have situations where you have 1, 2, 3 some power, you can have this with 2, 3, 4 and so on. Okay. So, this is the meaning of saying it is a all possible 3 cycles are the generators. With those generators you can create the whole, how many, what is the order of this group? Order of this group, someone, n factorial by 2, half the number. Okay. Conjugacy class is another question which you have to worry here. In the symmetric group of degree n, let us look at only the even permutation elements and see whether if they fall into a conjugacy class, do they still fall into the conjugacy class here. All these questions you need to check at least for permutation group of degree 4. Okay. If not for higher permutation, at least up to degree 4 you should have a feel of what happens. Conjugacy class we worked out for in the class for permutation of 5 objects, right. We drew the partitioning. For 4 objects you can write it out and see what are the conjugacy classes, and then which are the classes which are going to be elements of the alternating group, not all of the elements, right. Like for example, if I have a conjugacy class which is if you have this, it is 2 cycles, each cycle is a transposition, it is still allowed, it is an element of alternating group also. But if you had something like this, is this allowed? This is 1 3 cycle and 1 1 cycle, that is a cycle structure. So, this is what, even permutation or odd permutation? 3 cycle will have 2 transpositions, 1 cycle no transposition. So, it is even. So, you can start figuring it out which are the even transposition, which are the odd transpositions and so on. So, this one is probably not allowed, right. This is not an element of. Okay. Is that right? So, this way you can figure it out and also look at the number of elements. So, this also I passingly said bilateral axis, if the principal axis is in the plane of mirror symmetry, that is if it had a sigma v plane, that is the meaning, then the axis is called as a bilateral axis. Similarly, if you had a two-fold axis, which I denoted in the last lecture as u subscript 2, u2, if it is perpendicular, if the u2 axis is perpendicular to the principal axis, then also you call the principal axis as bilateral. Yeah, mirror plane basically. Mirror plane will have two directions, but both the directions, at least one of them should coincide with the principal axis. Which one coincides, I do not care. Okay. The mirror plane has to xz or yz, I do not worry, but it should have the z axis, which is the principal axis direction. Then you call it to be a bilateral axis. Okay. XY plane, if you had as a mirror symmetry and z axis as the principal axis, then you do not call it bilateral. Is that clear? CNV has a bilateral axis, n-fold symmetry axis, is that right? CNV and CNH, here you can call the n-fold axis as bilateral. Okay. Here n-fold axis is principal axis only, not bilateral. Okay. So, this n-fold axis is a principal axis and it is known as bilateral axis, but this one is not a bilateral axis. Similarly, if you take DN groups, they have principal axis, right, you also have a two-fold U2 which is perpendicular to, let me call this the principal axis Cn. Okay. So, if this is, in this case also you say that the principal axis is a bilateral axis. Okay. In both the cases, the n-fold principal axis will be called bilateral axis if there is an additional two-fold which is perpendicular to the principal axis, or if it has a mirror containing the principal axis. What is the advantage of defining a bilateral axis? Once you have a bilateral axis, then you can check, of course you can verify, but you can also say that if you do CKN, okay. So, if you take the principal axis, do it for Cn is the generator for rotation, n-fold 2 pi by n rotation. If you do it k times, you can always find some element in the group C and V, G inverse, which will be, this you can always find, where G is an element of, for example, okay. Yeah. No difference or anything. I am just saying the principal axis has another name which is the bilateral axis for both dihedral group and CNV group, but not for CNH group. That is all I am saying, no difference. Once you have a bilateral axis, even here you can show that so this is true for the DN, this is true for the, once you have a bilateral axis you can show that the elements are conjugates to each other. Which elements are conjugate? A C and K is conjugate to Cn n minus K. If you did not have the mirror plane, so C3 for example, what are the elements? identity C3, C3 inverse. It is an abelian group, right, and you can show that each element is a class by itself. Right. C3 is a class, identity is a class, and C3 inverse is a class. That is the C3 group, right. Suppose I go to C3V, what are the elements? Generators are C3 and sigma V, right, and then you have anything else? That is it. And you can show that sigma V C3 sigma V inverse is same as sigma V. You can show that this according to that property, what is it? It is C31 will be C32, C32 is nothing but C3 inverse. So, what happens now to the structure here is you have an identity union C3 C3 inverse, they form a conjugacy class by this, or this gets the threefold axis gets promoted to a bilateral axis. So, you have C3 and C3 inverse is the conjugate element, and what else? These are the, in the planes of symmetry, you started with one mirror plane, the C3 started generating for you the 3 mirror planes, right. Take a ammonia molecule, I showed you picture wise, there were 3 mirror planes. All these 3 mirror planes can also be shown to be conjugate to each other. Okay. So, essentially your C3V still has 3 classes like your C3, but there are classes with 2 elements, there are classes with 3 elements, and if you see it like a permutation group, you will call this as a 3 cycle, you will call this as a transposition or 2 cycle by isomorphism to symmetry. Okay. So, I am just trying to justify for you for C and V. I also want you to check for D3 what happens. Okay. I will leave it to you to check. Okay. So, I have tried to give you some flavor for C3V here, but I will leave it to you to check what are the conjugacy classes breaking like this for C4V, C5V, in general a C and V, and also to get some feel on dihedral groups. I have not done D3, but you can do it and generalize it to dihedral groups with an n-fold principal axis. That is the meaning of Dn. Okay. Okay. So, just to give as a result, dihedral groups distinguish between odd principal axis. If the n-fold principal axis is odd, then you find there will be p plus 2 1, then you have this one by using this property which I was talking now. Similarly, for Cn 2 and Cn to p plus 1 minus 2 and so on. So, there will be p classes for the principal axis symmetry which is 2p plus 1 fold symmetry, and you can see that these are like your various two-fold axes which are generated. Okay. S is like a two-fold operation. You see that those set forms a class together. Okay. So, do similar thing for D2P, you will see some difference there. The midpoint rotation, if you take D2P, sorry D, if you had D2P, clearly once I write D2P, the 2P fold axis is a bilateral axis, right. But what you can show is that C2P P is same as okay, that you will not find in the odd case. So, that is why there will be at least one midpoint element which is a class by itself. Like take C4V, C4V will have a C2 is a class by itself. Okay, so, there is slight difference between an odd and a even. So, the number of classes will increase by 1 or decrease by 1. There will be at least, I want you to check these parts. There will be some class, it is not only identity element, it is an element which has one element. You will also have a midpoint element which will be a element which belongs, which is self conjugate, that is what I mean. Okay. These elements R is conjugate to R2P, identity is self conjugate, but if P was even, 2P was, if you did not have 2P plus 1, if you just had 2P, then you will also find RP to be a class by itself. Okay. So, those are the distinctions. Okay. So, the other things which I want you to look at it is that I did show you some slides on cube symmetries which are having two-fold, four-fold and three-fold. This comes under the classification of octahedral symmetry. They denote the point group symbol as O for it. And similarly proper symmetry I mean only rotational symmetry, improper will involve reflection, inversion, all those combinations. So, regular tetrahedron, the methane molecule has a similar symmetry and you denote it in the point group literature by a capital T. Capital T is the tetrahedron symmetry. And then you can add improper reflection planes, and you have O subscript H, T subscript D. D is because you can generate diagonal mirrors, so you can write the conjugacy class and so on. So, these are the symmetries and you can start generating the conjugacy class for the tetrahedral symmetry, and TD is when you have the mirror planes and you will have rotoreflection. So, I will leave it to you. In fact, even in the Otterbein website you can start playing around on the methane molecule and get a feel of what is the TD group symmetry. Okay. Okay. So, this is where I left last time, that you can give a matrix representations. So, matrices which you can write, and then when you multiply C2 with sigma xz, you should get sigma yz, right. Is that right? C2 times sigma should give you this element. Is that happening? If you do the multiplication, it becomes minus, this becomes minus, no, this becomes plus and this is plus, right. So, it is having the group properties and you have a matrix representation. Can we write a matrix representations similarly? So, we did this also, I wrote it for the so suppose I have an object A1, A2, A3, and I do an operation, it goes to A2, A3, A1. Okay. So, can we write this element? What will be this element, somebody? Is this right? Am I right? So, these are the matrix representations you can write, which this is corresponding to like a 1, 2, 3 element in your permutation group, right. Suppose I want to write gamma 1, 2. So, let me call this here as 1, 2, 3. What will this be? Only 1 and 2 will get interchanged. So, clearly when I write all the elements, some elements will be diagonal, some elements are off diagonal. In this particular example of C2B, everything was diagonal, but sometimes you can take representations. These are also good representations for the symmetric group of degree 3. Okay. The question is that when you have these representations, do we need the fundamental minimal dimension of the matrices to be 3 by 3, or can it be lower? Okay. So, that is the question I am asking. Do we need the representations, or equivalently can I find a matrix S, some matrix S on, I should be able to write it in a block diagonal form. So, this is what I am calling it as a block diagonal. This is for all G, same S. S should be one S which breaks all the elements. Identity element is anyway in the block diagonal form, and S and S inverse will cancel, right. That is not enough. I have to find an S such that every element can be completely brought into diagonal. This is one possibility. It may not be possible to make it completely diagonal. You may be able to break it up into a 2 cross 2 and a 1 cross 2. Is there an S to do this? This is 1 cross 1, 1 cross 1, 1 cross 1. Is there an S to do this? One possibility is you can give it to the computer and ask it to figure it out. Another possibility is that we should be able to rigorously figure by some kind of a methodology, just like I did permutation group, and now you are comfortable with permutation group of arbitrary degree. If I write a 50 by 50 matrix, okay, whether it is can be brought to this form or this form, completely reducible, reducible as block diagonals. These are questions which one should be able to understand from a set of theorems and how to go about it. So, this similarity transformation will not alter the trace, that also you remember. If this trace is 0, by doing this transformation to make it into a diagonal or a block diagonal, you will not change the trace. Trace of the matrix will remain same. This operation will only tell us whether we can break this 3 by 3 into further fundamental blocks, which is what we call it as a irreducible blocks. So, this is the aim. Okay. So, let me stop here.